Already we have discussed about bootstrap sweep circuit. We have given a rectangular pulse. From that rectangular pulse, we have generated the sweep waveform. This is how we generated the sweep. Now we are discussing about Miller sweep circuit. This is also called as Miller integrator. We are taking a simple RC circuit. You can observe the resistor and capacitor. The combination of this RC circuit is connected as we discussed in the first chapter, RC integrator. So this is also called as Miller integrated circuit. Miller sweep circuit is also called as Miller integrator circuit. The main purpose of this circuit is to generate the sweep voltage. When we take this switch, when the switch is closed, the capacitor will not charge with this voltage or capacitor may discharge. When the switch is open, with the capacitor may charge. So this switch is used to generate the sweep. But the problem is, here we are not getting the constant current. In the bootstrap sweep circuit we already discussed, if we want to generate a very good sweep waveform, the current across the capacitor should be constant. So in order to make the current in the capacitor constant, we are adding a voltage source which we are calling as auxiliary voltage source. This auxiliary voltage source voltage is equal to the capacitor voltage. So it balances the capacitor voltage. By applying the KVL, we are taking the current is entering here. So when we are taking the current is entering here, this is minus V. The voltage here IR and the voltage here VC, because current is entering at the positive terminal, and this is minus VA because current is entering at the negative terminal. Summation is equal to 0. Because VC is equal to VA, the voltage across the capacitor is equal to auxiliary voltage source. These two terms will be cancelled. Finally, we get V is equal to IR, so I is equal to V by R. This indicates that the current in this mesh, the current in this circuit is independent of the capacitor value. The current in this circuit is depending on only voltage and resistance. Both these are constant. When voltage and resistance are constant, I is also constant. Because we are getting the constant current, there is a possibility of generation of linear sweep. So in order to generate the linear sweep, we are making sure that the auxiliary voltage source voltage is equal to the capacitor voltage. Then the constant current will be observed in this circuit. For my convenience, I am representing this circuit as this circuit. I am representing this circuit as this circuit. In this, we have taken the capacitor and auxiliary voltage source. Just I have shifted the capacitor to the above row, and I have shifted the VA, to the output side. We are calling this voltage as input. Now in the next step, we are representing here amplifier. The gain of this amplifier is minus infinite. We will discuss when we take the gain of this amplifier as the minus infinite, then the slope error will become 0. So in order to make the slope error 0, we are taking the amplifier with the gain minus infinite. So here V is same, R is same and capacitor is same. V in place of V in and V naught, we have samely we are representing, but only we have added the amplifier. In the next diagram, this amplifier, we are representing whatever the amplifier we have discussed here. This is having some input resistance, and this amplifier is also having the output resistance. So because this is having the input resistance we are representing with Ri, and the output resistance we are representing with the R naught. We expect for the ideal op amp or for any ideal amplifier, the input resistance should be maximum and the output resistance should be minimum. This is what we are calling as Miller sweep circuit, because we are representing here the switch we have added. This is switch we are using to generate the sweep waveform. But I am not interested in taking two resistances, R and Ri. I want to use the Thevenin's equivalent circuit. This is the Thevenin's equivalent circuit. Now I am applying the Thevenin's theorem. By applying the Thevenin's theorem, if I short this voltage source, then we will get to know about the Thevenin's resistance R dash. R dash is equal to the parallel combination of these two resistors, R into Ri by R plus Ri. The Thevenin's voltage is represented as V into Ri by R plus Ri. That's how we represented the Thevenin's equivalent circuit. The concept is remaining the same. A is the gain of this amplifier, and now we are representing the same circuit as transistor and op amp based circuit. Example you see here. In this case, when I am using the switch, in the place of the switch, we are using here the transistor. And similarly, when we are using this VI, AVI, in this place we are using the op amp. This is the op amp. So here, input we are giving V in. This is NPN transistor, and this is resistor. This is R dash, we have already discussed, R into Ri by R plus Ri. At t is equal to 0, at t is equal to 0 minus, we are not giving any input. At t is equal to 0, capacitor is not charged, so the output is 0. At t is equal to 0 plus, slowly the capacitor starts charging. The capacitor starts charging, and in what time the capacitor will be charged, that will be given by the time constant R dash C. This is R dash, this is C. If the time constant is low, capacitor will be charged fastly. If the time constant is more, capacitor will be charged slowly. The capacitor tries to charge exponentially, but we are trying to make it as a linear waveform, because the current we are expecting it should be constant. When the current is constant, we may expect the linear waveform. So this is how the capacitor may give the output like this, non-linear. But we are trying to make this as a linear by giving the chance to flow the constant current across the capacitor. At t is equal to infinity, the capacitor acts like an open circuit. Then if Vi is equal to V dash, then V naught is equal to AV dash. Because we are using the op amp in the inverting mode, this time the sweep will be observed in the fourth quadrant or in the negative side, negative voltage. Because we are connecting the input to the inverting terminal of the operational amplifier. This is how we are successful in generating the linear sweep by using the Miller sweep circuit. In the Miller sweep circuit, we already discussed, we called this Miller sweep circuit as Miller integrator. In this Miller integrator, we have started our concept with this simple circuit. In this simple circuit, because we are calling as integrator one resistor and capacitor and supply V. As we are saying it should generate the sweep, we are taking the switch S, that's all. But the problem is, this circuit is generating the sweep, but that is not linear. So in order to maintain the linearity, we have to make sure that in this circuit constant current is flowing. The current should not change. For that we are adding an auxiliary source to this circuit, and the voltage of this auxiliary source is equal to capacitance voltage. So this will balance the capacitance voltage. Then the final current in the circuit is V by R. Current in the circuit only depending on the V and R. So this current is constant. Now in this circuit, just I have shifted the capacitor and the auxiliary voltage source. I have represented with the help of the amplifier. And in this amplifier, we have considered the input resistance and the output resistance. And then we added the switch here. We have taken the Thevenin's equivalent, V dash and R dash. Finally, we are replacing it with the operational amplifier. And we are replacing this switch with the transistor. Transistor is acting like a switch, and this is op amp. At t is equal to 0, we have discussed the capacitor is not charging, so V naught is equal to 0. At t is equal to 0 plus the capacitor slowly charging. Because we have connected the input to the inverting terminal of the operational amplifier, we will observe the output sweep in the negative side. This is how op amp based Miller sweep circuit will work.